Today, I will be talking to you about improvements on a bronze plating project. To begin, the setting of the product would be in plating shops or in wet processing departments within a company. The customers of this plating process would be, more specifically, bronze platers. This could include aircraft companies, decorative platers, and more. The top customer needs are to have an effective masking tool, to have the plated bronze adhere to the sample or part, and to have an effective rack design. In my ethnology study, I noticed inefficient and ineffective masking tools. The tape and paint being used to mask the sample could not withstand the plating environment adequately. I also observed that there was a need for better adhesion between the base metal and the plated bronze. The middle photos show the plated bronze simply popping off of the sample. Finally, an effective rack design is necessary to produce uniform plating. In the picture on the right, it can be seen that there is a buildup of plating on the edges, a high current density area. A more effective rack design would minimize this to create more even plating. My simplified axiomatic design can be viewed here. As discussed, the main customer need is to plate bronze and to have high quality plating, an effective masking tool, and adhesion. The functional requirements include maintaining chemicals, providing uniform heat, and covering areas that do not require plating. These lead to the design parameters of creating a reusable mask, creating a properly balanced plating process, and uniformly plating. This axiomatic design led me to my design overview of an improved bronze plating process. The total design of a bronze plating tank is shown in the design overview. For the masking tool, the tape and paint method currently being utilized as a mask is not effective. To solve this, a plastic mask can be created. This will be made out of a heat shrink type material, but will still be reusable with the proper material and tolerances built into the design. A reusable mask will decrease the masking time and will save money in material and labor. This design can be used for the test sample as shown, but the design can also be modified slightly in the future for part masking. The design of this particular mask will be used throughout production as an adhesion test. The plating process requires heat regulators, pulse plating rectifiers, a proper rack to hold samples and parts, and an automatic chemical addition system. These items can increase the quality of plating immensely. The pre-processing steps required are also crucial for the adhesion of the plated material to the base metal. These steps are covered in the storyboard of the design. Additionally, the racking tool will be designed to hold the anodes close to the plating surface for uniformity. The day in the life of my design begins with a test sample or part needing to be plated. First, the part or sample is masked with a reusable masking tool. Next, the plating area is cleaned by abrasive blasting, cleaned with an organic cleaner, rinsed, activated with acid, and then struck with nickel. The part is positioned on the rack and lowered into the plating tank by hand. The part is pulse plated for 96 hours in the tank. This is in contrast to the usual constant amperage plating. The tank is held at a constant temperature of approximately 130 degrees Fahrenheit, a lower temperature than previous experiments of 160 degrees Fahrenheit. This will allow more uniform plating to occur and will be controlled by multiple heat sensors added to the tank. The heat sensors will encourage uniform heating throughout the tank and constant temperature. This will further increase the quality of plating. Because this is a long plating process, there is also an automatic chemical addition supply to replace used chemicals. The chemicals that are depleted during the process are cyanide and tin. Finally, after the 96 hours, the part is removed from solution and demasked. The mask will be reusable for multiple runs because of the tolerances incorporated into the design, allowing for shrinkage in the material. The part is placed in the ovens at 375 degrees Fahrenheit for 16 hours for hydrogen stress relief. One design alternative was to design a masking tool alone instead of an entire plating process. However, the idea of having a plating process with consumables is more appealing to both customer and manufacturers. The customer can have a turnkey solution and the business can have a continuous customer instead of a one-time customer. The design alternatives for the process include using off-the-shelf heat shrink tubes. This is a more labor-intensive masking idea, and these are not reusable. Another design alternative is to use a brush plating method instead of the in-tank plating method. This may be effective for decorative platers with a low thickness requirement, but for this application, it was not realistic or safe. Thanks for watching and listening.